back, everyone. So what we learned so far, we learned about relations. We said that, hey, a relation is a relation like R is an equivalence relation if it is reflexive, symmetric, and transitive. Reflexive, symmetric, and transitive. Okay, perfect. So now we're saying that, hey, if we have a relation and that relation is an equivalence relation, we're interested in defining a representative that show us what do we have in each, for example, partition. So definition, let R be an equivalence relation on set A. We define something as a representative for each of those classes or sets that connects all the data, all the values, all the objects that are connected together through that relation. So here we define an equivalence class, for an element. So we have an element like A in A, and we define equivalence class for that element. This equivalence class is denoted by bracket A, we open and close the bracket, which is equal to the set of all X values in A such that those X values are in relation with A. X is in relation with A. So this is equivalence class of A, which is equal to the set of all members such that those members are in relation with A. Or you can write, hey, this is the set of all elements in A such that X and A is a member of R. So this is the official definition of equivalence class of A. So what are we doing? Suppose this is set A. This is an element like A. We are having all those elements that are in relation with A in one partition. X, Y, Z. The rest of the elements that are in relation with A in one set. We might have other elements that are not in relation with A, so they form another partition. Let's write down this definition on the right-hand side. So equivalence class of A, element of A, is equal to the set of all elements in set A such that X is in relation with A. This is equivalence class of A. Example. In this example, the set is given as A equals to, well, what do we have here? 0, 1, 2, 3, 4. 1, 2, 3, 4. We have a set. We define a relation this way. The relation R is defined as R equals. Again, remember that a relation is a collection of ordered pairs. We have 0 and 0. We have 0 and 4. We have 1 and 1. We have 1 and 3. We have 2 and 2. We have, let's see, 3 and 1. We have 3 and 3. We have 4 and 0. And we have 4 and 4. Well, now the question says, find the equivalence classes of R. Find the equivalence classes of R. So what's the meaning of that? It means that for each element in A, it means that for each element in A, we can write the class this way. The first element is 0. What is the equivalence class of 0? What's the set of all elements in A such that X is in relation with 0? What is this? What's the equivalence class of 1? The second member of A is 1. It means that what is the set of all elements in A such that those elements are in relation with 1? X is in relation with 1. What's the equivalence class of 2? What is the set of all elements in A such that X is in relation with 2? And finally, we have 3 and 4. What's the equivalence class of 3? What is the set of all elements, members of A, such that X is in relation with 3? And finally, the last member is 4. What is the equivalence class of 4? Or what is the collection of all elements in A such that those elements are in relation with 4? So, equivalence class of 0 is the collection of members of A such that those are in relation with 0. So what is in relation with 0? 0 is in relation with 0. What else? 4 is in relation with 0. What else? That's it. So this is going to be the set of 0 and 4. What's equivalence class of 1? All the members of A such that they are in relation with 1. So what are those numbers in A that are in relation with 1? Okay, 1 is in relation with 1. What else do we have? 3 is in relation with 1. Okay. We have 1 and 3. Equivalence class of 2, all the members of A such that those numbers are in relation with 2. What is in relation with 2? 2, okay, what do I have? 2 is in relation with 2. So this set has only one member. Do I have more colors? Hopefully, these two. Equivalence class of 3. What is in relation with 3? Okay, 1 is in relation with 3. What else is in relation with 3? 3 is in relation with 3. So here you have 1 and 3. Okay, what is in relation with 4? With 4, 0 is in relation with 4, and 4 is in relation with 4. 0, and 4. Okay. What do we see here? Equivalence class of 1 and equivalence class of 3 are the same. Do they have the exact same members? Some lemmas. Our lemma says so suppose A is a set and R is an equivalence relation on A. Equivalence relation on R. Suppose A and B are two members of set A. Well, if A is in relation with B, for sure their equivalence classes are equal to each other. What's the meaning of that? It means that the set of all members in A that are in relation with A is equal to the set of all members in A, let's call them Y, such that those elements are in relation with B. So in general, if R is an equivalence relation on set A, for A and B in set A, you have the following. Equivalence class of A is equal to equivalence class of B. These two sets are equal to each other, or these two sets have nothing in common. They are disjoint from each other. So these two sets are equal or they're disjoint from each other. They are disjoint. They don't have anything in common. There is no way you can say that, hey, they have, for example, one element or two elements in common to each other. They're either equal or they have nothing in common. That's why if we have an equivalence relation on a set, actually form a partition for that set. So note that an equivalence relation, a set defines a partition on that set. It means that if you have set A, you can define partitions. These partitions are including equivalence class of A, equivalence class of B, equivalence class of C, equivalence class of D, equivalence class of E, and the rest of them. And note that A is not in relation with B, C, D, A, and B, and C, and D, and E are not in relation. Well, recall that. Recall that if A and B are integers, and n is greater than 1, then we have the following. We say that n divides A minus B. It means that n is a factor of difference between A minus B. And we define it this way. There is an integer like k such that A minus B is equal to n times k. And we define this way. A is congruent to B mod n. And at the same time, we can write A as B plus nk. And what's the meaning of that? It means that if we divide A by n, it has a remainder. Whatever that remainder is equal to the remainder when we divide B by n. When we divide A by n, the remainder is the same as the remainder when we divide B by n. Mathematically, we write it this way. A mod n is the same as B mod n. Again, remember that in programming, when we're talking about the mod operator percent, it means that we are working with the remainder. Mod or the remainder. The remainder of A divided by n is equal to the remainder of B divided by n. These are all equivalent to each other. N divides A minus B. It means that n is a factor of A minus B. N is a factor of A minus B. It means that there exists an integer like k, that A minus B is equal to nk, or A is B plus nk. What's the meaning of that? Another definition, another notation that we use is A is congruent B mod n. What's the meaning of that? It means that if we divide A by n, the remainder is equal to the remainder when we divide B by n. So these are all equivalent to each other. When we're talking about n divided by A minus B, it means that the remainder are equal to each other. Very well. So recall that we define congruous mod n to be an equivalence relation. Okay, so we have two recalls. Recall that congruence mod n is an equivalence relation. We also define something new. So also recall that for set A and an equivalence relation on A, we define equivalence class of members of A this way. The set of all x values in A such that x is in relation with A. Well, naturally, I expect you to ask that, okay, we know that congruence mod n is an equivalence relation. This can be R. How do I define equivalence classes using this equivalence relation? So, for our equivalence relation R, which is congruence mod n, we can define equivalence classes this way. Equivalence class of A, which is defined as the set of all elements in A such that x is in relation with A. This relation is now replaced by the congruence relation. This is equal to the set of all elements in A such that x is congruent to A mod n. We just replaced this relation by congruence mod n. What's the meaning of that? So it means that A, equivalence class of A, is equal to the set of all elements in A such that n divides x minus A, or this guy is equal to the set of all elements in A such that x minus A is equal to n times k. K is an integer, or this is equal to the set of all elements in A such that x is equal to A plus n times k. So using this equivalence relation, we can define equivalence class of members of A this way. Very well. So let's write this down here. We're going to have another definition. So we're interested in creating a new set, and we try to define some operations on that new set. So what we learned so far, let's write them step by step. We learned that we have an equivalence relation. Then a congruence mod n is an equivalence relation. Since we have an equivalence relation, we can define the equivalence classes of members of set A. So equivalence class. And since we have congruence mod n as an equivalence relation, we can define equivalence class of members of A as the set of all elements in A such that x is congruent A mod n. Or another notation using the definition is x equals to a plus nk. K is an integer. Very well. Now we're going to take all of these distinct equivalence classes and form a new set. This is our goal. Our goal is to take all of distinct equivalence classes of our equivalence relation congruence mod n of our equivalence. The relation. This relation is congruent mod n and define a new set. And define a new set. Okay, this set is denoted this way. Z sub m, Z sub m, which is equal to the set of all of these distinct equivalence classes. 0, 1, equivalence class of 2, equivalence class of 3, the rest of them, and this is stopping at equivalence class of m minus 1. The set of all distinct equivalence classes of this equivalence relation congruence mod n. This is a new set. On this set, we can define addition and multiplication. Isn't that interesting? We create a new set, a new word, and now we can define some operations, addition and multiplication. We define addition this way. Equivalence class of A plus equivalence class of B is defined as taking the equivalence class of their sum. And multiplication is defined this way. A equivalence class of A times equivalence class of B is defined as equivalence class of A times